We'll wait for a few minutes for others to join. Okay, let us start the session. Welcome everyone to the second week of the NPTEL tutorial for the course Fluid Mechanics. So just hold on. Yeah, I think great. So my name is Varnit Kapoor, and I'll be taking the tutorials for this course. So in the past week, we have completed up till different kind of viscosities. The last topic was this only about dynamic viscosity and kinematic viscosity. And we have seen that how dynamic viscosity of water is higher, 50 times higher than that of a gas, or air particularly, whereas kinetic viscosity of water is less than that of air. Okay. So one question a student asked in the last class, that how the temperature will play a role when the density is different for different fluids. So let us start with that topic only in today's class. Let me share my screen. I hope my screen is visible. Can anyone of you confirm, please? Hello?
Yes, sir.
Am I audible? Yeah. Is the screen visible? All right. Great. So in the week 2, let us start with the topic effect of temperature and pressure on the viscosity. Okay. So there are two kind of viscosities. First is kinematic, first is dynamic, second is kinematic. Okay. So first one is dynamic, and it is defined both for liquid as well as gas. Liquid as well as gas. Okay. So we have seen that with increase in temperature, what happened to the viscosity of liquid? So with increase in temperature, the viscosity of liquid decreases. Just trying to join. Okay. So with increase in temperature, viscosity of the liquid decreases. Why? Because cohesion forces or the intermolecular forces starts breaking in the liquid when you increase the temperature. Because cohesive forces starts breaking. Okay. Whereas in gas, with increase in temperature, the viscosity of gas increases. With increase in temperature, how? We have seen this through kinetic theory of uh, gas expressions as well. So viscosity of the gas increases, and it is directly proportional to under root of temperature. Under root of temperature. So when the temperature increases, gas viscosity increases. Why? Because more momentum transfer take place. More momentum transfer takes place. Okay. So this was a reason for dynamic viscosity. Okay. We have seen this thing, but coming to the kinematic viscosity section. So coming to the kinematic viscosity, nu. So it is again defined for both liquid and gas. So again for liquid as well as gas and gas. So with increase in temperature, first of all, we will see that with increase in temperature, the what is dynamic kinematic viscosity? Kinematic viscosity is dynamic viscosity to that of density of that fluid. Okay. So with increase in temperature, let me write here. With increase in temperature, the kinematic viscosity. Let me separate it by a line. Not this. So it's fine. So mu of the liquid increases, or let us write like this. Dynamic viscosity is nothing but mu of liquid to that of density of liquid. So what happens basically with increase in temperature, we have seen here that liquid density decreases. Sorry, with increase in temperature, the mu of liquid decreases. We have seen here. Okay, with increase in temperature, mu of liquid decreases. So what will happen to the kinematic viscosity? This will also decrease. Now, few people will ask, what is the effect of on the density? So for liquid, with the increase or decrease in temperature, density is very uh, less amount of reduce. Like we have seen in the previous tutorial as well, that for 0 degrees Celsius, it was 1000 kg per meter cube, whereas for 20 degrees Celsius, it's what 998 kg per meter cube. So it was very minor change in the density. So it's, you can say, more or less negligible change. So there is no change in the density of the liquid with increase in temperature. Whereas for the gas, mu of gas to that of rho of gas. So what happens? We have to see the effect here. So what happens? You know that for an ideal gas, what is the expression? Let me write here. For ideal gas, if you assume that your gas is ideal gas, and when does the ideal gas is said to be in which state? Low pressure, high temperature. We have studied in thermodynamics, that thing. And if some of you have not studied thermo properly, you can check my tutorials of the previous semester. So on my channel. So pressure is nothing but PV is equal to MRT, or you can say P is equal to density into R into T. Density into R into T. So here you will see that your density of the gas is dependent over both pressure as well as temperature. So what we will do, we will study the effect of pressure and temperature separately. First of all, so what we'll do, we will study the effect of temperature and pressure separately. So when we are studying the effect of temperature, we will keep the pressure constant, and when we are studying the effect of pressure, we will keep the temperature constant. Okay. So if you see here, density is inversely proportional to temperature. From the above relation, density is inversely proportional to temperature. Okay. So you know that kinematic viscosity of gas is nothing but mu of gas, and mu of gas is nothing but directly proportional to under root of T. Okay, under root of T. And density is inversely proportional to 1 by T. So let me write it clearly in steps, then only you'll understand. So kinematic viscosity of gas is mu of gas by rho of gas. Okay. Now you know that rho of gas is inversely proportional to T, whereas mu of gas is directly proportional to root of T. Okay, from kinetic theory. So what you can do, you can use these two expression and put it here. Okay. So what you will get, nu of gas is directly proportional to root of T by 1 by T. Okay. So you can say it is directly proportional to T to the power of 3 by 2. So kinematic viscosity of gas is directly proportional to temperature to the power of 3 by 2. Temperature to the power of 3 by 2. And here the temperature is in absolute terms. Absolute temperature we are talking about. So with increase in temperature, your kinematic viscosity of gas also increases. Okay. So here pressure was kept constant. Point to be noted is that pressure was P is equal to constant, and effect of temperature is observed. Okay, first thing. Now, so we can make a table here. Okay, what I can do here is that I'll make a table to concise. So I have 3 columns and 3 rows. Okay, so first says that temperature, then liquid, then gas, and here it says that mu, that is dynamic viscosity and kinematic viscosity. So we know that with increase in temperature, what will to happen to the viscosity of liquid, dynamic viscosity? Will it decrease or increase? Please tell me. With increase in temperature, what will happen to the dynamic viscosity of liquid? We have just seen here.
Decreases. Sir, decreases.
It will decrease. As well as what will happen to the kinematic viscosity? It will also
Decrease.
decrease. Okay, we have done here now. So with increase in temperature, both kinematic as well as dynamic viscosities decreases. Both kinematic and dynamic viscosity decreases. Okay, whereas with increase in temperature, what happened to the dynamic viscosity of gas? It increases because molecular momentum increases. We have seen here with increase in temperature, mu of the gas increases, as well as now we have seen that with increase in temperature, kinematic viscosity of the gas also increases. Kinematic. So these both increases. All right, clear? Any doubts? Any doubts still here to anyone? Yes or no?
No, sir.
Great. Okay. All right. So what we can say that with increase in temperature, liquid viscosity is both decreases, whereas gas viscosity is both increases. Okay. Now we will see the next thing. We will keep temperature to be constant and see effect of pressure. All right. Let us see. Two, for both the cases, for kinematic viscosity as well as dynamic viscosity. So once we will see for the dynamic viscosity, we can see for both the cases like liquid as well as gas once again. So for liquid as well as gas. So if you increase the pressure, I think liquid viscosity doesn't changes. It is independent because there is no expression like P is equal to rho RT there. So mu of liquid is not a function of pressure, because liquid is generally incompressible in nature, where we will define a property called as bulk modulus, and I'll explain that thing also. We have seen in the first tutorial that when you try to compress the liquid, it resists a lot, whereas a gas doesn't resist much. Okay, so it is more of incompressible in nature. So I can say that if you have a liquid and you try to compress it, it will be incompressible. Okay, so density is not function of pressure. That means density is not function of pressure. If density is not function of pressure, then there is no change in the kinematic viscosity as well. Okay, there will be no change in the kinematic viscosity also. Let's come to the gas part here for the dynamic viscosity. So mu of gas is directly proportional to under root of T. There is no expression of pressure here. We have seen from the kinetic theory of gases expression. The expression was under root of 3 kT by m. Okay, so there is no pressure here. So it is not the function of pressure. So both dynamic viscosity for both liquids as well as gas, they are independent of pressure. There is no dependence over the pressure. Whereas for the kinematic viscosity of liquid as well as gas, so if you increase the pressure here, what will happen to the liquid? We have seen just now that, sorry, nu of liquid, let me separate it. Yeah. So nu of liquid is nothing but mu of liquid by density of liquid. And we have seen that there is no effect of density as well as of the dynamic viscosity. So there is no effect on the change in the dynamic viscosity of kinematic viscosity of the liquid. Whereas for nu of gas is again mu of gas to that of rho of gas. And we have seen from here that mu of gas is independent over the pressure. When you increase the pressure or decrease the pressure, the dynamic viscosity of the gas doesn't vary. So there is no change here, but there will be a change here. How there will be a change? Since you know that since pressure is equal to rho RT, so this implies density is directly proportional to pressure of the gas. So density of gas is directly proportional to the pressure of the gas. So if you increase the pressure, density also increases. So you can say that the density increases and the kinematic viscosity decreases. Kinematic viscosity decreases for the gas. Is it clear or any doubts in understanding? So again, I'll make a table here for your short understanding. Is that again 3 columns, 3 rows, but this time pressure will play a role. Here again liquid, gas, and here will be dynamic viscosity and the kinematic viscosity, dynamic as well as. So we have seen that with increase in the pressure, there is no effect on liquid. There is no effect on liquid for kinematic as well as dynamic viscosities. Whereas with increase in pressure, dynamic viscosity of the gas doesn't changes, but kinematic viscosity of the gas decreases. Kinematic viscosity of the gas decreases. All right, any doubts in this, understanding this? Does anyone has any doubts for understanding the effect of pressure and temperature on the viscosities? I don't know who asked that question in the last lecture towards the end, but is it clear now?
Yes, sir, it is clear.
Clear? Okay, great. I want everyone to be active. If you have any doubts, please stop me and ask me. Okay? Don't hesitate to ask. Okay, great. So if there is no doubt, we can proceed further. All right. So now let us move to the topic of linear velocity assumption. When you can assume that your velocity is linear, behaving linear in nature. Okay, linear velocity assumption. Linear velocity assumption. I hope you all have received a mail from the NPTEL about the class recordings and the material. So you might be able to access the first tutorial video, which was already uploaded on my YouTube channel, as well as the Google Drive link where the week 1 PDF notes has been uploaded. Were you able to access that?
Yes, sir.
Great. So don't worry about the notes. If new students have joined, don't worry about the notes. I always share these PDFs. Even the NPTEL team will also share the link with you in the sheets. So you can simultaneously write down as well as you can just listen. Main thing is you should focus what I'm teaching. Okay, so linear velocity assumption. So when we say, let me again make a, okay. So here it is a plate and fluid is flowing over it. So I'm making a velocity profile. So we have made a velocity profile in the last tutorial. That velocity profile looks something like this. And if linear profile assumption only happens when there is a condition where it is very near to the wall, when the fluid is near to the wall, for the fluid near to the wall. So if I assume that fluid was flowing in hole, but I am assuming only very thin portion of the liquid which is flowing near to the wall. Okay, so that means this line is nothing but something like a linear in nature. And this distance is how much? This distance is how much? Small h. This distance is how much? Small h. So in this region only, I will assume that my linear assumption will happen to the velocity. Linear assumption. I can apply. So what do I mean that if I just project this into a macroscopic form, this here. So what I'm trying to do is basically again my plate. So I'll make a plate here that it is a wall. So I'll make a plate This is my plate, and this was the smaller thickness. I have zoomed it, okay, and this distance was h. Okay. So what I'll do, I'll say that I have zoomed it. Okay, so I've zoomed it. So this distance is h. So what you can say that this is the increasing y direction upward, and here the velocity is assumed to be increasing linearly. So what happens, how the velocity profile looks like? So it looks like something like this. So here some, initially it is no slip, just at the boundary, then some velocity, then some velocity, then some velocity, and then some velocity. So what does it mean? Velocity is, what do you mean by that? Velocity is linear. What do you mean by velocity is linear is that the rate of the deformations phi from the vertical phi, all are phi, all are constant phi. Okay, got it? So all are equal to phi, all the phi's are same. I'll write here, all phi are, all the phi are same. That is deformations. All the deformations are same. So what do you mean by linear profile distribution? Suppose velocity distribution, sorry, u is equal to a plus by. In mathematical terms, your velocity is behaving a linear assumption, a plus by. So from the boundary condition, if y is equal to 0, your direction y is 0, that means it is a solid wall. At y equal to 0, your velocity is 0. Put these values, you will get the a is also equal to 0. If you put y0, u0, your a will also come out to be 0. Next is when y is equal to h. When y is equal to h. So that means my velocity here is constant, that is v. Suppose v. So u is equal to v. So this implies your b will be v by h, because this has already become 0. This is v and this is h. So b will become v by h. V by h. So put a and b. So therefore your velocity profile will be, therefore u is equal to v by h into y. V by h into y. So this is your linear velocity profile assumption. So for a small thickness, when the fluid is flowing over a plate, so for a very small thickness, your fluid is behaving linear profile assumption. Linear profile assumption. So here the velocity was u. Suppose, let me use a circular. But here it is velocity v, and the rate of deformations are constant. Rate of deformations are constant. So we have seen an expression that is shear stress is directly proportional to mu into du by dy. We have seen this expression in our previous tutorial. Put the u here, put this u here. So it will be mu into e of dy of mu y by, sorry, vy by h. Sorry, vy by h. So if you differentiate, it will be mu v by h. So therefore you can say that your shear stress is mu v by h. And all these values are constant. Mu is constant for a liquid. Mu is constant for a liquid. Velocity is constant at the upper layer. H is constant, that is the thickness. So all of this value is constant. So what will shear stress profile look like? What will shear stress profile look like? So if I want to make a shear stress profile, it will be looking like a constant value. Constant value and opposite to the direction of flow, because it is a resistance to the flow. Shear stress profile will something look like this. Tau. It's a constant value. Okay. Is it clear? Shear stress is not a function of y here. This implies shear stress is not a function of y, whereas velocity was a function of y, which is a linear function of y. Linear function of y. But shear stress is not a function of y for a small thickness, h, where I'm assuming linear profile assumption. But we have done one question in the last tutorial where we had seen that for increase, when you are going above in the direction y, your shear stress decreases. So that was above the linear profile assumption. That scenario was for above the linear profile assumption. So let us write that here as well again. So you again make a velocity profile distribution like this. So this is your velocity profile distribution. So suppose that your first layer is this is u, and this is u plus du. So this is velocity u, and this is u plus du. Whereas this is u dash, and this is u dash and u plus du dash. Okay, u plus du dash, and both have same thickness. You can say both have same thickness dy. Okay, both are same thickness. So what can you observe if I draw a vertical from a graphical formation? If you see here, the angle is between them is d phi, and here the angle is d phi dash, So which angle is bigger, d phi or d phi dash? D phi is bigger or d phi dash? By observing,
D
say
phi.
d phi is bigger, right? You can observe that d phi angle is bigger than d phi dash. So you can say that your d phi dash, that is your, basically it is the shear strain rates only. So d phi dash by dt is less than d phi by dt. Or you can say in terms of du by dy. This implies du dash by dy is less than du by dy. Because we have seen that d phi by dt is proportional to du by dy. We have seen this in the last tutorial. And if you multiply both sides with viscosity, so it will be mu, because viscosity of the fluid is same on both the sides. Mu du dash by dy is less than mu du by dy. So this is nothing but your shear stress. So shear stress away from the wall is less than closer to the wall. Okay. Shear stress away from the wall is less than closer to the wall. So how we can express this graphically, this thing? How we can express this graphically? So I'll again, for your reference, I'll make one graph. Is that what I want to say? If you observe this, sorry, if you observe this, not like this, make like this. So this is your y direction. Your velocity profile looks like this. So here your angle was, those who have not understood, here your angle reformation was d phi by dt. So if you take some another point like this angle will be this. If you take some another point, this angle will be this. If you take some another point, this angle will be this. And this is d phi dash by dt. And you can observe that d phi dash by dt is less than d phi by dt. So at y is equal to 0, your d phi by dt is maximum. So that means your shear stress is maximum. Shear stress is maximum, and that is not nothing but called as wall stress. Wall stress over the fluid, wall, W. Okay. And how we will draw the velocity profile for this as well as shear stress profile together? How we'll draw the velocity and shear stress profile together? Let me draw. So velocity profile is looking like this again. So this is your velocity profile. Okay. Velocity profile distribution. And your shear stress profile will look something like this. Let me make till here. At the wall, it is maximum, then it goes on decreasing, then it goes on decreasing. Okay, so this is your shear stress profile, and this is your y direction. and shear stress here is maximum. Tau is maximum at the wall. Tau is maximum at the wall, and this is shear stress. Oh, sorry. Profile. Okay, great. So we have done one example in the last tutorial where we have seen the example was that velocity profile was given like 3 by 4 of y minus y square. What is shear stress? It is mu du by dy. If you differentiate it, it will be mu times 3 by 4 minus 2y shear stress. So if you increase y, your shear stress is gonna decrease. With increase in y, if you're moving in upward direction, the shear stress is gonna decrease. Okay, clear? Any doubts about understanding this topic? Any doubts?
No, sir.
What about others?
No,
Afroz?
sir.
Abhiraj has also no doubt. Afroz? Simran? Suryansh? Do you
No,
have
sir.
doubts?
No,
No
sir.
doubts? Great. Okay, great. All right. Okay. Now, let us come to the next topic of lift and drag. Lift and drag. So on a general body, there are two forces acting on the fluid, forces acting by the fluid on that body. Okay. So one is because of the horizontal component as well as the vertical component. Okay. So, and these two, horizontal and vertical, can occur because of the pressure as well as the shear force. So let me draw here. If I have an arbitrary shaped body like this, okay, and a fluid is flowing, that is u infinity. Okay. So what is happening? A pressure is acting on the body. A pressure is acting on the body. Okay. As well as shear force is acting over the body. As well as shear force is acting over the body. Just like this. Okay. So if I draw the components of the pressure force, the horizontal and the vertical component, this is FP. So this will be FP horizontal and FP vertical. And if I draw the components of the shear force, this is Fs, shear force. Okay, so horizontal and component. So there will be a body can push forward as well as lift up. A body can push forward as well as lift up. Why it will push forward? Because of the net horizontal forces acting. The net horizontal, this horizontal and this horizontal are together acting, and they are trying to push the object further because of the fluid which is flowing. Whereas the vertical forces provide the lift. This force and this force can be of unequal in nature and can provide a lift, or can be equal in nature and doesn't provide any lift. Okay. So what I can say, my drag that is pushing, F drag, happens because of net horizontal forces, net of horizontal forces, and my lift happens, lift, F lift happens because of net of vertical forces on that body, So I'm assuming that it is happening over a very small elemental area. So pressure forces pressure into area only. Okay, so you can assume that this is happening over a very small elemental area, that is dA. dA, small elemental area. I'm studying over a very small area. So drag FD will have force due to pressure, elemental force integrated over the surface in the horizontal direction, whereas shear force into area integrated over the entire surface of horizontal component, whereas lift force is because of the pressure in the vertical direction plus shear stress force, pressure force and the shear stress force in vertical direction. Okay, so that is the main crux of lift and drag happening over a body. Okay, lift and drag happening over a body. Now there are three kinds of bodies, three kinds of generalized bodies which we will study. So first is a thin body. A thin body or okay, first we'll see the thin body only. So thin body, what does a thin body is? That is of negligible thickness. So area will be 0 for that. Thin body like this. It is very thin. There is no thickness over the body. I think I've made it bigger. Okay. So there is no thickness. So area will be 0. If area is 0 on that, so here area of this area is 0. So here pressure PdA, pressure force, this is 0. So pressure force will be overall 0. There is no pressure force when fluid is flowing from here, u infinity, okay, for a velocity. But shear force will be there. Shear stress will be there. Shear stress into area, that is dA. If you took of elemental area, the shear stress is acting over a parallel area. So this will be this area, okay, complete this area. Whereas the pressure force was acting on an elemental area this much, but this is of negligible thickness. So that is why it is 0. That is why it is 0. So there will be shear stress eventually, shear stress eventually. So what is happening? Only a net horizontal force is acting. There is no net vertical force. There is no net vertical force. If there is no net vertical force, that means your lift is 0 on that body. FL is 0 and only drag is there. Only drag is there. Only drag is there. F drag is there. Okay. So net only by, and this is only because of the shear stress only. Shear stress only. Net only by shear stress. Since P into dA is equal to 0 as dA is 0 for pressure to act. So this kind of body is called a streamlined body. This kind of body where only a drag is happening over a thin body, that kind of body is called a streamlined body. Streamlined body. Let me write. Streamline body. Okay. All right. Next kind of body is called as bluff body. Bluff body. What is a bluff body? From the name, it suggests that it's just going to do some bluff with us. So if you have a body like this, okay, and velocity of the fluid is coming like this. Fluid is coming like this from a velocity u infinity. So again, there will be a pressure force on this, that is P into dA, and the shear force will act parallel to the surface, that is shear stress into area, whereas here also shear stress into area. But if you observe, both the shear stress are cancelling out. Here again, lift is 0. FL is, F lift is 0 because upward shear stress is cancelled by the lower shear stress. and only drag is happening. Drag is happening. Only and only drag is happening. F of drag net only because of the pressure force. Net only by pressure. Okay. So net effect of shear stress in since net effect of shear stress into area is equal to 0. That cancels out. That cancels out. Okay. So that is why it is only having a drag force, no lift forces here. It is not lifting. Okay. Next kind of is a general body. Suppose you can say that an inclined kind of scenario where you have body like this. So here again a fluid is flowing, and here will be drag as well as lift because of both pressure and shear stress force, horizontal and vertical components. So where this kind of body is observed is generally seen in aeroplanes. If you see the wings of the aeroplanes that are tilted, if you have set or seen the aeroplane, the wings are tilted so that you are able to produce lift as well as drag in that. So that aeroplane can push forward as well as lift up in the air. Okay, so that's why wings of an aeroplane are tilted to generate lift and drag. Okay, lift and drag. Okay, any doubts in here in this to anyone? Does anyone have any doubts?
No, sir.
No doubts. Can anyone tell me that this statement is true or false? When there is lift, there will always be drag, but when there is drag, it is not necessary lift will be there or not. When lift is there, drag will always happen, but if drag is there, it is not necessary that lift will happen or not. Can anyone tell me, is this statement true
Sir,
or false?
I think it is true, sir.
It is true. Why?
Sir, because in these three cases, there is, sir, in some cases there is no lift, but in all cases, drag is present.
Drag is there. Correct. Correct. So if you see in the third case, lift is there and drag is also there. But if you see in the above two cases, drag was there, but lift was 0. Okay. So drag is here as well, but lift is non-zero. But here drag is there, but lift is non-zero. So whenever lift is there, drag will always be happening. But whenever lift is there, drag will always happen. But when drag is there, it is not necessary. If drag is here, it is not necessary lift will be there because here it is. But here drag is there, but lift is not there. Here drag is here, but lift is not here. Okay. So vice versa is not true. Okay, great. So I'll write this statement, very important statement. Note, when there will be lift, there will always be drag. But not vice versa. Okay, but not vice versa. All right. I hope there are no doubts still here. Now let's come to the concept which everyone was waiting, I hope. That is Newton's law of viscosity. We have studied so much things, but we have not started from the Newton's law of viscosity. And most of that I don't know about others. Various people just start with this only. What is Newton's law of viscosity? But the student should have a very basic fundamental knowledge for coming till here. So topic, Newton's law, viscosity. So what does Newton's law of viscosity states? So as per Newton's law of viscosity, shear stress is directly proportional to the rate of shear deformation between two layers. Okay. So that means that viscosity of the fluid is independent the rate of deformation to the rate of deformation. So whatever we were doing till now, that is shear stress is directly proportional to du by dy. This is nothing but your Newton's law of viscosity only. But I have to give you the essence of physical flavor of the science, what is happening, that why we are doing this all. So this was nothing but the Newton's law of viscosity so far. Okay. So I'll write this. As per Newton's law of viscosity, shear stresses directly proportional to rate of shear deformation between two layers, that is viscosity of fluid is independent the rate of deformation to that of rate of deformation. Okay. All right. So it is similar like if you have studied strength of material, it's similar like Hooke's law. Okay. Hooke's law. So where I draw the plot, where I've drawn the plot also last lecture. So in the linear profile regime, shear stress is directly proportional to shear strain for solid objects, but for liquid, it is shear stress is directly proportional to a rate of shear strain. So it says nothing but shear stress is directly proportional to du by dy, and that is nothing but equal to mu du by dy, where mu is nothing but your viscosity, and it is directly proportional to viscosity is a fluid property, and shear stress is directly proportional to gradient of velocity or shear strain rate. Shear strain rate. So I can draw plot like this. Here I have shear stress, and here I have shear strain, or you can say du by dy. And it is, we are talking about the linear regime. Here, your mu is constant. Mu is constant, but shear strain is happening. So all it is for a single fluid only. Mu will be constant. Okay. So what is slope of tau by tau, and what will be the slope of this graph? It is nothing but viscosity, dynamic viscosity, and it can and dynamic viscosity for different fluids can be different. For honey and water, honey has a higher viscosity compared to that of water. So what will a graph look like in that scenario? Again, make a plot for different fluids. So it will be something like, so this is for mu1, this will be for mu2, and this will be for mu3. The slopes will be different. So if mu1 is highest, that means it is a higher viscosity fluid. If the slope is high, that means a higher viscosity fluid. And these are nothing but your Newtonian fluids, because they are following Newton's law of viscosity. You are saying that Newton's law, that is the linear regime. So example of Newtonian fluids: for Newtonian are water, air, most of the gases, kerosene, gasoline. Okay. Now the question comes: classification of fluids. How many kind of fluids can be there? How the fluids can be classified? Classification of fluids. So first is Newtonian and other is non-Newtonian. Newtonian, another will be non-Newtonian. So from the name, Newtonian are basically the whole fluid mechanics. We are going to deal with Newtonian fluids only. Okay, in this course. So tau is directly proportional to mu du by is equal to mu du by dy. Okay, these are Newtonian fluids where your shear stresses versus du by dy have a constant slope. Have a constant slope, that is mu. Whereas non-Newtonian can be classified based on the function of pressure and time. Okay, sorry, on the function of velocity gradient and time. So first is the one where your viscosity, I am saying viscosity apparent. I'll tell why I'm saying this. Mu apparent is not the function of time, but is function of mu apparent is function of gradient of velocity du by dy. And these can be classified into three. One is dilatant, others is pseudoplastic, and next is Bingham plastic or ideal plastics. These are the names of the fluids basically. So first is dilatants, next is pseudoplastics, and third is Bingham plastics, or you can say them ideal plastics as well. Okay, and those fluids under non-Newtonian category, which are function of both velocity gradient and time, are mu apparent, that is function of both velocity gradient as well as time. That with time also the viscosity changes. So these are basically categorized in two various ways: thixotropics and rheopectics. Rheopectics, thixotropics, and next is rheopectics, rheopectics fluids. Okay, so this is a general classification of the fluids, and they don't follow, both of them don't follow, tau is not directly proportional to du by dy, not directly proportional to, because they are not following Newton law of viscosity. Okay, any doubts still here? Any doubts to anyone? No doubts?
So apparent,
I'll explain the apparent. Don't worry.
yes. So
I'll explain what is apparent viscosity. Apart from that, any other doubt?
No, sir.
Okay. I'll just take a short, a minute or 2 minutes of break, and then we will resume. Just be in the class, just a short break. I'll be back in a minute or two.
So,
Sir,
Sir,
you are
you are
not
muted.
audible.
Sir, you are muted.
Am I audible now? Hello?
Yes, sir.
yes, sir.
Oh, great. Sorry for that. Let me again share my screen. I hope my screen is visible now
Yes, sir.
and I'm audible. Okay, great. Okay, so I was saying that non-Newtonian fluids are nothing but those are not following Newton's law of viscosity. So they are following some another law for shear stress and gradient of velocity relation. So let us generalize that. So for non-Newtonian fluids, non-Newtonian fluids, the shear stress is nothing but, suppose, B plus K times velocity gradient du by dy to the power of n. Let us say it is a general. N is a flow behavior index. N is a flow behavior index. Let's say this is a general experimental scenario. Let us say that let B is 0. If B is 0, your shear stress is nothing but K times du by dy to the power of n. We can bifurcate this in terms like du by dy to the power of n minus 1 into u by dy. And this, my friend, is nothing but your mu apparent, so that we are having a relation mu apparent somewhat like Newton's law of viscosity, du by dy. Okay, make sure that mu apparent is not the mu of that velocity fluid. It is k times du by dy to the power of n minus 1. Okay, this is your mu apparent, and b is nothing but your a constant for a, if you have a relation y is equal to mx plus c, that c is nothing but your constant there. And similarly here b is equal to constant. We have assumed that for a case scenario where b is 0. Okay, now we will draw the plot for shear stress versus du by dy, and we will see what are the mu apparents in all the cases, how the mu apparents will change. Very important plot I'm going to make. So okay, so this is shear stress, this is du by dy. This time your slope of this will be mu apparent only. Okay, mu apparent. So let me first make, then I'll explain each plot one by one. So Newton's law of Newtonian fluids are basically these, where mu is constant. Dilatants are those where mu apparent increases. These are your dilatants, and these are your pseudoplastics. I'll write here. These are Newtonian. These are dilatants. These are pseudoplastics. I'll explain, don't worry what they signify. So these are those where your mu apparent, I should not write make like this, I should use blue color. So here it will be mu apparent, and here it will be mu apparent. So if you observe, for dilatants, your viscosity mu apparent is increasing with increase in the gradient, velocity gradient. Whereas pseudoplastics are those fluids where your viscosity decreases, mu apparent viscosity decreases, okay, with increase in the velocity gradients. Okay, but Newtonian fluids are those where the viscosities are constant for that fluid. Here it will be only mu, only mu. So these are your pseudoplastic and dilatants. I'll give the examples as well. So first let me frame dilatants. Dilatants. So dilatants are those shear stress versus du by dy, and these are your dilatants. Okay, so here if you see this, let me first write apparent viscosity increases with increase in deformation. Am I audible to everyone?
Yes, sir.
Yes, sir.
Okay, increase in deformation. So what do I mean? What was our relation? B plus K times du by dy to the power of n. Here if you observe, there is no constant b. B will be 0 here because our plot is starting from origin. So here b is 0. B is 0. So our shear stress is nothing but mu apparent times du by dy. And mu apparent is K times du by dy to the power of n minus 1. So to increase viscosity, mu apparent continuously, this is your mu apparent. If you want this to be increased, you want this term to be increased. You want this term to be increased. And how this term can be increased? If this is a positive value. If this is a positive value. So what I can say that your n minus 1, this implies your n minus 1 should be greater than 0. That means your index, fluid flow index, flow behavior index, flow behavior index n should be greater than 1 for dilatants. Okay. What are these solutions? What can be the example of dilatants? Honey, sugar solution, butter solution, quicksand. So if you stir the honey, if you take a honey and you stir it, deform it, will it get thicker or not? And or you say a quicksand, basically daldali mitti. We say na that we should not move our hand very fast if you are stuck in a quicksand. Otherwise, it will sink you inside it. So wherever the rate of deformation is more, the shear stress will be increasing more. If you try to rotate honey, you will feel more and more amount of pressure. Similarly for sugar solution, butter solution, and quicksands. Example are honey, sugar solution, then butter solution, and quicksand. This is nothing but dilatant. What are pseudoplastics? Any doubts in dilatants? Does anyone has any doubts? Someone try to unmute. Please say if you have any doubts.
No, sir.
Okay, great. No doubts. So pseudoplastics. So what color you use? Green. Okay. Shear stress versus du by dy. So pseudoplastics are those where with increase in gradient, your shear stress decreases. Shear stress increases, but with increase in gradient, your viscosity decreases. Okay. Your viscosity, that is mu apparent, decreases. Here it is higher, here it is lower. Whereas in the above scenario, it was initially higher, then again higher, much higher, like that. So here, if you see, tau is again b plus mu apparent du by dy. So b is 0 here again, starting from origin. So for what is mu apparent? K times du by dy to the power of n minus 1. So for mu apparent to decrease with increase in du by dy, if you are increasing in du by dy and your mu apparent should decrease, your n minus 1 should be greater or less than 1? Greater or less than 1?
Less than 1.
Your n minus 1 should be less than 0. Sorry, greater than
0.
less than 0. So n is less than 1. Then n will be less than 1. So what are the examples of this kind of fluid? If you see your blood, milk, polymer solution or colloidal solutions. Okay. If you stir the blood, it will get much thinner and thinner. That is why if you see in the labs, blood testing labs, they put your blood samples inside a centrifugal rotator kind of machine so that your blood gets thin and all the platelets and the other blood cells get separated from the plasma and other kind of thing. I'm not a medical guy, but I know the science behind that is that when you try to deform very fast, it gets much thinner and thinner. Viscosity decreases. Similarly for milk, polymer solution and colloidal solution. Okay. Example, blood, milk, colloidal solution. And these above all were non-colloidal. Okay. All of these were non-colloidal. Okay. And here colloidal solutions. Okay, we have understood Newtonian dilatant pseudoplastics. Now let us make Bingham. So Bingham are those are similar to Newtonian, but here B will non-zero. Are similar to Newtonian only. Let me make. These are Bingham or idle plastic. Bingham. The thixotrophic will be like this. Use some other color. These are your thixotrophics where your mu apparent decreases and B is also non-zero. Thixotropic. Okay, these are thixotropic. And these are your rheopectics. This is your mu apparent. Here this was your mu apparent. These are rheopectics. So if you observe here, in all these scenarios, there is some constant shear stress, tau E. Okay, so here some constant shear stress is there. That is B is non-zero in these scenarios. B is non-zero. So Bingham, first let me write Bingham. Bingham or idle plastics. So shear stress and du by dy and Bingham are like this. So there is some part is there where the fluid is behaving like a solid initially, tau E. Okay, and after that it will be mu. Okay, so tau is nothing but B plus mu apparent du by dy. So here B is non-zero. B is non-zero and B is equal to tau of E. Some shear stress is initially required. And mu apparent is again du by dy to the power of n minus 1. And here it is constant. So for this to be constant, mu apparent to be constant, this value need to be constant. That means n minus 1 should be 0. N minus 1 should be 0. So that is n will be a constant value. That is 1. N will be a constant value. That is 1. Okay. So again, it is similar kind of Newtonian fluid only, but with some initial B value. Okay. What are the examples of such kind of fluids? Toothpaste. So initially you say when the toothpaste is inside the your bottle or case, initially it somewhat behave like a solid if you hold it. But when you try to press your toothpaste, then after some initial stress, it start to behave like a normal fluid, like water. So toothpaste. And when you do your brushing, it became like a water kind of thing. Toothpaste, gels, okay, creams, or you can say drilling mud or clay suspensions. Drilling mud or clay suspensions. Next is thixotropics. So when you start brushing initially, what happens? The for Bingham plastics, I am saying it starts making a foam or froths, and it is a continuous kind of thing. Okay. Thixotropics. Let me make this shear stress versus du by dy. So I've used the pink color for thixotropics. So this is starting not from origin, and this is your mu apparent. This is again decreasing. Mu apparent is decreasing, and initially there is a value that is tau e. So again, B is non-zero here, as well as B is equal to tau e in this case, and it is same like pseudoplastics again. Same like pseudoplastic, with there n was less than 1. And here also, if you do, n will be less than 1. Same kind of graph, just not starting from origin. Just not starting from origin. What are the examples of thixotropics? Your ketchups. What happens with time with the ketchups? They see, first of all, dependent on the gradient as well. When you try to deform from the bottle your ketchup, it try to become liquid, viscosity decreases. Okay, and with the time, how the thixotropic will look like, I'll frame the time graph also. This is just dependent over the gradient. So here n will be less than 1. Examples: ketchup, paints. Initially paint is very thicker, but when you try to rotate that paint, it becomes very water-like. Enamels or sewage sludges. Okay. Next are rheopectics. So I'll frame the graph for this. Tau versus du by dy. So again, these look like not starting from 0, mu apparent, and it goes on increasing. So here B is tau e, and here again it is similar like a dilatant, n will be greater than 1. What are the example? So if you see printer's ink, and you try to push it, initially it is a fluid, but when you try to push it, what happens? Or gypsum solutions are there. It get much thicker in nature. Gypsum, try to deform some solution. Now, rheopectics and thixotropics are dependent on time as well, along with deformation. So what happens to the ketchup if it is kept for long amount of time? Does it get more thinner or thicker? You have been eating your ketchup since your childhood. What happens to the ketchups?
Thicker, sir.
Thicker. Are you sure?
Sure.
Others? Karthikeya, what do you say on this? Does your ketchup get thicker or thinner with time?
Sir, I think it will become thinner.
Thinner. So we have observed in nature that when the ketchups are kept for too long, they get more of a liquid-like. Okay, they get wasted. So with the time, the viscosity of thixotropics decreases. Whereas for the paints, if your paints are there, okay, for the printer ink is there, not paints and ketchups are same. If your printer ink is there, even if you see for paints also, not ketchup, if you keep your paints for a long amount of time, they get thinner with time. Okay. Whereas for printer's ink, if it is kept for a long amount of time, that ink get dried up and thicker. It loses its moisture and get more and more thicker. So how, with respect to time, the viscosity of thixotropic and rheopectic will look like? So mu apparent with the time. So if I make my thixotropic will look like what? Decreases thixotropics. This is mu apparent plot with respect to time. Okay. And your rheopectics viscosity will increase. I hope it is clear. Any doubts to anyone? Any doubts?
No, sir.
No doubts. Now let us make a short note. what are viscous and non-viscous flows? Okay. Always remember there are two things in fluid mechanics. One is fluid and another is flow. So when I'm saying flow, what does it mean? And when I'm saying viscous and non-viscous flow, okay? So non-viscous flows are those flows when viscosity is there, but viscous action is absent in that, okay? Where fluid has viscosity, but viscous action is absent because of that viscosity, okay? And viscous flows are just opposite, okay? Viscous flows have viscosity as well as viscous actions. So when do you observe this kind of scenario? Let me draw a flow over a plate kind of scenario. So this is a plate where my fluid is flowing at a where a viscous fluid mu is flowing. Fluid is viscous always at a velocity of u infinite. So as you know that when the fluid flows, some layer forms initially because of the presence of the wall. Okay. And we make a velocity profile like this. We make a velocity profile like this. This is your velocity profile. So initially during that layer, this layer is nothing but called as boundary layer, and we will cover this boundary layer. Don't worry. This is a layer because of the presence of your boundary or the wall. So some part of the fluid will have uh, this velocities, gradient of velocities will be present. Why? Because of the no slip condition. Wall, no slip condition. We have seen this. U plus du, then some another velocity here. Okay. Whereas above the boundary layer, all your velocities will be u infinite only. But here it will be u, here it will be u plus du, and so on. Okay. So if you observe in this scenario, here there is no change in the gradient. All of the layers are having velocities to be same above the layer, above this boundary layer. Above this boundary layer, all the, I can make, I'll not say anything, I'll just say it's a layer and short form boundary layer. Okay. Above this boundary layer, all the velocities are of the fluid are same. So there is no change in the gradient. Okay. So no change in the gradient, that means mu times du by dy is also equal to 0. This implies shear stress is 0. That means viscosity of fluid is there, but no viscous action is there. Shear stresses are 0. Such kind of flows are called as non-viscous flows. So above the layer, they behave as a non-viscous flow, whereas inside here, shear stress, sorry, let me first write, gradient of velocity is non-zero. This implies mu times dy by dy is non-zero. This implies shear stress is non-zero. So such kind of flows are viscous flows. Okay. And these are non-viscous flows. Okay, non-viscous flows. So there is one equation that is a Bernoulli equation, which is nothing but sum of all the heads is equal to 0, pressure, kinetic, and datum head. So Bernoulli equation is always applicable. Make sure outside this boundary layer. That is for non-viscous flows. Okay, and be peculiar. I'm saying non-viscous flows, not non-viscous fluid. Fluid is viscous; it has a viscosity, but the flow is non-viscous. So our point to note here is that I'll explain this Bernoulli equation and everything later in our later sections. Bernoulli equation is applicable outside boundary layer. That is, this implies for non-viscous flows. That's why I've written flow in highlight, and not non-viscous fluid, since fluid is viscous, it has some viscosity. Okay, I hope this point is clear to everyone. Any doubts? Yes, Abhiraj, you have raised your hand.
Sir, a few minutes ago you said that ketchups are thixotropic fluids, right? So why they are thixotropic? Why are they not pseudoplastic fluids?
So if you don't deform the ketchup at all initially, it will be at rest. It will behave. If you have a solid bottle, okay, if you have a solid bottle inside the bottle, plastic bottle, your ketchup is there. If you don't deform at all, it will behave somewhat like a solid cap. That is, there is no deformation, but so you need initial pickup for the deformation, and after that, after some amount of deformation, shear stress, the deformation will start in the ketchup. That's why you have to squeeze it initially. If you just keep it like this and you expect that ketchup should drop down, it doesn't happen easily. If and make the scenario it is in the vacuum, pure vacuum, because initially on Earth gravity is there. If you keep that bottle of ketchup inverted open, the ketchup will not flow at all. It will be like that. You have to just squeeze a little bit. If you are in a pure vacuum scenario, then the ketchup will start to come out and start, because of her more deformations, it will start to deform. That is why it is a thixotropic, not a pseudoplastic. Is it clear
Oh, okay, sir.
in practical? Yeah. Okay. Anyone else have any other doubt? Okay. So I was talking about non-viscous fluids, non-viscous flows, not fluids. Okay. Now I'll talk about what is an ideal fluid. We have so far understand Newtonian and non-Newtonian fluid. What is an ideal fluid? Ideal fluid. So ideal fluid is that fluid which has a viscosity 0. There is no viscosity of the fluid. Mu is 0. No viscosity of fluid. And on our planet, there is no such fluid doesn't exist. Okay. So viscosity, that is, no cohesive forces are there. And if no cohesive forces are there, surface tension will also be 0. Okay. In that scenario. So there will be no boundary layer. If viscosity is 0, then how come viscous action can take place? Viscous action only takes place when viscosity is non-zero of that fluid. Okay. So this implies no cohesive forces and also sigma is equal to also 0 in such scenarios. So how this fluid will look like when you flow that over a plate, flow it over a plate. So if your fluid is flowing over a plate, we can imagine how this fluid will look like, and it doesn't have a viscosity. Viscosity is 0 of this fluid. How will it look like? It will look like just layers of fluid going, with all of them having equal velocities. Okay. There is no boundary there. No boundary there. Because there is no viscosity present. So there is no resistance of the fluid. Okay. So such kind of fluids are called ideal fluid, and they doesn't exist in reality. Okay. So I'll make a final plot again of shear stress versus du by dy or d phi by dt. So ideal fluid is nothing but where there is no viscous action. Shear stress is 0. So if you see, there is no shear stress present here. So this is your ideal fluid. Whereas solids behave where deformation, rate of deformation is not there. Solid have a deformation. I told you in the first class. Solids have deformation, but it has a constant deformation. It doesn't have a rate of deformation. Fluids are those which have constant rate of deformations, not constant. These are elastic solids. Okay. In the first lecture itself, starting was from this only, difference between solids and fluids, if you remember. Okay. Any doubts still here?
No,
So
sir.
here strain will be there, but no strain rate for the elastic solids. I'll write this point. Strain will be there, but no strain rate. Okay. Okay, now let's come to the other topic, that is bulk modulus. Bulk modulus. So what is a bulk modulus? It is nothing but a measure of elasticity of the fluid. Measure of elasticity of the fluid. Okay. So, and it is inverse of the compressibility. Inverse of the compress. So bulk modulus plays a role when you try to compress a fluid. Viscosity plays a role when you try to provide a shear force to the fluid. Okay. So far we were understanding about the viscosity and the shear forces. Now we'll come to the compressive forces when we apply a compressive force over a fluid. So it is a measure of modulus of elasticity of fluid. It is inverse of compressibility. That is, higher the bulk modulus, lower the compressibility. Okay. So liquid have large value of bulk modulus because they are less compressible in nature, whereas gases are more compressible, so it has lower value of bulk modulus. Liquids have large value of bulk modulus. That is, K of water is 2 into 10 to the power of 6 kilonewton per meter square. Okay. Whereas with respect to gases have low Kw, that is 101 kilonewton per meter square. Okay. So liquids are considered as incompressible with respect to gases. So liquids are considered incompressible with respect to gases. Okay. So let us take a scenario of a cylinder kind of scenario, and there is a piston in that cylinder. So this is a cylinder filled with fluid and it has a piston. Okay. You provide a pressure on this piston such as P. So it will try to compress the fluid inside it to a scenario where you can say that here, and your pressure has increased, which will be P plus dP. Okay. So this is the change in the volume happened, dV. Okay. All right. This is your change. So if your change in pressure is greater than 0, that is your initial pressure, final pressure is higher than the initial pressure. That means your volume change, final volume, suppose this value, final volume is nothing but V plus dV. So your final volume will be less. Final volume is V plus dV, which will be less than dV. Oh, sorry, V, which will be less than V. Okay. So initial volume was V. It was having a much higher volume compared to the final volume. So that means your dV is less than 0. Your change in volume is negative. That means your volume has decreased. By increasing, pushing the piston in the cylinder, which has a fluid inside it, your volume has decreased. Volume has decreased. So what we can say that your change in pressure is directly proportional to change in volume with respect to initial volume. With respect to initial volume. So if you increase the pressure, your volume, change in volume is decreasing. Decreasing. Okay. So what we can say that this value will be a negative value because dV is negative, and change in pressure is a positive value because we have seen that change in pressure is a positive value, whereas dV is a negative value. So if your dP, change in pressure, is positive and this value is negative, this value is positive, this value is positive, this value is negative. So your dP is equal to the bulk modulus K into, you have to provide an extra sign, negative sign, so that it becomes positive, dV by V. K times minus dV by V to make dP to be positive. So this is your relation, that is K, dP is equal to K times minus dV by V. Any doubts that how with respect to pressure change your volume changes? Any doubts? Yes, no?
No,
No,
sir.
sir.
No? What is the doubt? Okay, no doubts. Okay, great. All right. So your bulk modulus is nothing but dP by negative of dV by V. This is your bulk modulus relation. Now I want this dV by V in terms of density. Density. How can I write? Since we know that density into volume is nothing but mass. Differentiate this. If you differentiate this, since mass is always conserved, differentiation of mass will be 0, and this can be differentiated by chain rule. Rho dV plus V d rho is equal to 0. So here, from here, dV by V, sorry, d rho by rho, d rho by rho is nothing but negative of dV by V. And put this back here. Your bulk modulus will become, in terms of density changes, K is equal to dP by d rho by rho. And this rho is the initial rho. So for a gas, density can change very easily compared to that of water. Okay, compared to that of water. Clear? Any doubts?
No,
So
No, sir.
this is your bulk modulus, and compressibility is inverse of bulk modulus, or bulk modulus is inverse of compressibility. So compressibility beta is inverse of bulk modulus. So I'll write symbol of bulk modulus is nothing but K, and compressibility has a symbol of beta. Okay, beta is inversely proportional to K. So this is 1 by, put this relation here, dP by d rho by rho. Okay, dP by d rho by rho. So your compressibility can be written as 1 by rho dP by d rho. 1 by rho dP by d rho. So this is your compressibility. Compressibility. Okay. Now, for an incompressible fluid, your compressibility will be, what will be the compressibility? If your fluid is not compressible, what will be compressibility?
0.
0. Great. For an incompressible fluid, And point to be noted here is that I'm always talking about fluid so far. This bulk modulus is defined for fluid. Compressibility is defined for fluid. Incompressible fluid. I'm not saying anything about flow. Just hold on, guys, please. Hello, am I audible? Hello, hello.
Yes, sir, you are.
Audible, sir.
Yeah. Oh, sorry for the uh, disconnection. My Wi-Fi got disconnected. Just hold on, please. Okay, I'll share my screen. Is my screen visible now?
Yes, sir.
Hello? Yeah, great. Yeah, so I was saying for my incompressible fluid, the compressibility is zero. Beta is zero. Okay. So if beta is 0, what does it mean? That means your dp by d rho should be 0. Am I right? Sorry, I did a wrong relation. It is dp by d rho by dp, right? It will be d rho by dp. Okay, so my d rho by dp will be 0. Okay, very important relation. That my change in density with respect to pressure will be 0 for the incompressible fluid. Incompressible fluid. Okay, and what will happen to my bulk modulus? My bulk modulus will be infinity, and there is no such fluid which cannot get compressed in reality. The fluid can get compressed even a small amount. Okay, but we won't say that it is totally like compressible. It can change, but a very less. So we say in general scenario, it is incompressible in nature. Okay, incompressible fluid in nature. Okay, it cannot get compressed. Okay, no doubts. So far I was talking about for the fluid compressibility and bulk modulus. So temperature tells about the expansivity, that how it can expand, whereas pressure tells about the compressibility. Okay. Now coming to bulk modulus for gases. Bulk modulus for, this was for bulk modulus of liquid, bulk modulus for gases. So again, if you push in the piston cylinder arrangement, and the pressure volume plot follows like, if I want to plot a pressure volume plot, a gas either follows PV is at a temperature constant, your PV is equal to constant, or PV raised per gamma is equal to constant, any adiabatic or polytropic relation. Okay, so it will be like, it cannot be like pressure can be constant, then volume will not change. If volume is constant, that means pressure will not change. So that cannot be a scenario for a gas to get compressed from a state of P1 to P2, P1 to P2, or P1 to V2. Sorry, P1 will be this. This is V2, and this is V1 from V to V2. This is your state 1. This is your state 2. So it can compress because of the two relation, either because of temperature is equal to constant, then it will be PV is equal to constant, or a relation P by rho to the power of gamma is equal to constant, or PV raised by gamma is equal to constant. So there are two relations. One is isothermal bulk modulus for this gases, or adiabatic bulk modulus. Okay, two relations will be there. Isothermal bulk modulus, isothermal K. So we know that P is equal to rho RT. So if you differentiate it, dP by d rho is equal to RT, and if you multiply both sides by density, rho dP by d rho is equal to rho RT. Okay, so this is nothing but your bulk modulus, rho dP by d rho. So this is your bulk modulus K, and it is equal to rho RT, and rho RT was nothing but P. Rho RT was nothing but P. So it is K is equal to P. So bulk modulus is P, whereas compressibility beta will be 1 by P for an isothermal bulk modulus scenario. For an isothermal bulk modulus scenario. Whereas for an adiabatic bulk modulus scenario, we know that relation follows P is equal to rho to the power of gamma into constant. Again differentiated, dP by d rho is equal to gamma times C rho to the power of gamma minus 1 from differentiation. it will be nothing but gamma times C into rho to the power of gamma. Okay, getting my point? Into what? Tell me.
-1.
If it is gamma minus 1, and if I multiply both sides by dp by d rho. So this rho into the gamma minus 1 into rho will be gamma times C into rho to the power of gamma. Okay, and this is nothing but your bulk modulus K. Okay, and what is this? C into rho to the power of gamma. It is P. It is P. So K is equal to gamma times P, and this implies your bulk modulus will be 1 by gamma times P. Okay, so for a adiabatic bulk modulus is nothing but gamma times P. Isothermal bulk modulus is pressure only. And this is for gases I'm talking, not liquids. Any doubts?
No, sir.
And if you observe that compressibility for an adiabatic compression is less than that of an isothermal. So why? Because this will be a higher value, so compressibility will be less, whereas this will be a lower value, so compressibility will be more. Okay. All right. Next, what is a Mach number? Note, what is a Mach number? Mach number, MA, is nothing but speed of sound in the liquid to that of speed of sound, speed of the fluid to that of speed of sound. Okay, so Mach number is nothing but V by C. All right, so C, that is nothing but your speed of sound. Speed of sound is defined as under root of K by rho. Under root of K by rho. K is your bulk modulus to that of density of that fluid, of that. Whereas for solids it is elasticity by rho. For liquid it is K by rho. So for a liquid, C is K by rho. And what is bulk modulus for a liquid? For a water, what is bulk modulus for water? I have written above. K of water was very high, that is 2 into 10 to the power of 6
6.
kilonewton per meter square, and density was 1000 kg per meter cube. If you put these values, your C of water will come out to be 1414 meter per second. So speed of sound is 1414 meters per second. Whereas for gases, C is nothing but again K by rho, and here two Ks are there, one for isothermal and one for adiabatic. So in isothermal scenario, K is P, so it will be C is equal to P by rho, and P by rho is nothing but root of RT, okay, given by Newton, and this was given by Newton. Whereas for adiabatic, K is gamma times P, so C will be under root of gamma P by rho. So that is C is nothing but gamma RT, gamma RT, and this was given by Laplace. This was given by Laplace. Okay, is it clear?
Yes, yes, sir.
So when a fluid is flowing through a duct, okay, or a channel, then there will be a flow of the fluid which will happen. And for a flow to be incompressible, your density change should be less than 5%. Should be less than 5% in that scenario. Okay. So for incompressible flows, density change should be less than 5%. For incompressible flows, note. Now I'm talking about flows, not fluid. flow, my change in the density with respect to initial density should be less than 5%. And what is V by C? V by C, it is nothing but 2 times, V by C is Mach number, and it is nothing but 2 times d rho by rho, under root of 2 times d rho by rho. Okay, so this comes from a Bernoulli relation. When you do a Bernoulli relation, you have a water tank, and at this point and this point you apply a Bernoulli equation, your V by C will come. So that we will do in the later part. So V by C less than 2 times d rho by rho. And what is d rho by rho? Less than 5%. So should be less than 2 times 0.05. Correct? So that means Mach number should be less than 0.32. So if Mach number is less than 0.32, that is your condition for incompressible flow, although your fluid is compressible in nature. Okay, this is a condition when flow is incompressible, but fluid is compressible. Okay, for air, Mach number is V by C is less than 0.32. So their speed of sound is 332. If you put above in the values, gamma RT and RT, these values, speed of sound come out to be 332 to 334. So here velocity will be less than 106 meters per second. So for incompressible flow of air, your velocity should be less than 106 meter per second. I'm saying this is fluid, not liquid. Fluid is compressible. Gas can be compressible. Air can be compressible, but flow is incompressible. So last point to note here is that for incompressible fluid, flow will always be incompressible. For incompressible fluid, if a fluid is incompressible, like liquid, fluid, flow will always be incompressible. Be incompressible. But for compressible fluid, flow can be compressible. Can be compressible if Mach number is less than 0.32. But for compressible fluid, flow is incompressible if Mach number is less than 0.32. Is it clear or any doubts?
Yes, sir.
No doubts?
No, sir.
Great. So we will end up the session here, and you will get the recordings of this session through the NPTEL team, as well as all these recordings I will upload on my YouTube channel. That is, the name is, my YouTube channel name is NPTEL with Varnit. And in the video description, you will get the link for the PDF, Google Drive link. And you can also share among your batchmates who are interested to watch the video lectures about my YouTube channel, or they can also enroll in the NPTEL course. So I think there is no doubt. Maybe we can end the session, and on the next Tuesday, I'll see you at the same time, 6 p.m.
So,
Alright.
sir, where the PDF can be downloaded?
Either you'll get the link from the NPTEL team, or in my video description, the link of the Google Drive will be there on my
Oh.
YouTube channel. Okay.
So,
Yes, Karthik.
Sir, does every fluid contains both viscous flow and non-viscous flow?
In every,
Sir, does every fluid contains viscous and non-viscous flow?
most of the fluids can be there with viscous flow and non-viscous flow.
Okay. Thank you.
But if fluid is incompressible, then there will be, then what will happen?
Then there will be non-viscous flow will not be present.
So every fluid will have a viscous and non-viscous flow. Apart from the boundary layer, it will be non-viscous flow. Inside the boundary layer, it will be a viscous flow. Okay. Any other doubts?
No, sir.
Great. So I'll stop